All right, so welcome to this video. It's a very nice video on a solution and explanation from Resnick and Halliday. There are two trains which are given in this question, and one train, which is the fast moving train, is moving with 161 kilometers per hour. So this is a train which is moving with a speed of 161 kilometers per hour, right? And what has happened is a train has entered its path by mistake, okay? And this train is moving with 29 kilometers per hour. And these two are approaching each other like this. And when the driver, this driver, the driver of the high speed train, okay, which means the driver here doesn't care. The driver here is in the fast moving train, applies the brakes, okay, and the way he has to apply the brakes is that he's just able to avert the collision, right? So which means they almost come very close to each other. So this is your high speed train. Let me draw a diagram and say this is your high speed train engine, and then this is your the other train, which I will use the other color so that you can distinguish. They just touch each other, right? They're almost like touching each other. Okay. And so if you notice this question, the direction of motion, okay, is also known. So the fast moving train and the slow moving train, right, which is entered by mistake, are moving in the same direction. And this is very important point that you should know. So this is your fast moving train and this is your slow moving train, right? SMA is slow moving, okay? Now, how do we solve a problem like this? What are the concepts we have to use? I find these questions to be very interesting because they have some practical value inbuilt, and real life you will see that this happens, and it's very interesting to solve these questions. All right, so there may be multiple approaches that may come to your mind. I will just tell you the logic, the way you need to think about this. See, there is a concept of relative motion, right? Relative motion. So what you do in relative motion is you transfer the speed of the body, one body to another and subtract it, right? So which means if this body is moving with 29 kilometers per hour and this body is moving in 161, it is as good as saying that the fast train, which is the fast train, is moving with 161 minus 29. Okay, so 161 minus 29, 231. Okay, so 132 kilometers per hour. So you can assume that the fast train is moving with 132 kilometer, and since you have transferred the speed of the slow moving train to the speed of the fast moving car with a negative sign, you subtract it. This is moving now with 0 kilometer per hour. So it is one and the same thing. You can say that one is moving with 161, the other is moving with 29, or you can say this is moving with 132 and this is moving with 0. It is one and the same thing, right? So which means what I've done is I have made this stationary. So this is now stationary, as good as stationary. I have transferred its velocity using the concept of relative motion. Why did I do this subtraction? Relative motion. You can go and watch my video on relative motion. Interesting numericals given out there, which are very, very useful. Okay. Now the distance between these two is how much? The distance between these two is 100 and no, sorry, it's not 100. It's just about 0.676 kilometers. I have converted everything to kilometers, okay, because speeds are in kilometer and all. Right, so the first concept I've used is the concept of relative motion because it really eases my life. It makes my life very simple because I can use the concept of relative motion where it transferred the speed of one body to the other. Please understand relative motion. Very important topic for your upcoming examination in school, NEET, JEE, AP Physics, SAT, IB board, whichever part of the globe you are. These questions are very important. Learn about them. All right. Now the interesting part of it, right? So this train then moves, the faster train, which is now having just a velocity of 132, it continues to move, and it has to stop just before, the first slow moving train, which is now stationary in our case, and result and should not result. When we say, just avoid the collision, this is where it stops now. Okay, practically it stops very close to the other train, right? So there is no distance between them. So the net is that the speed of this particular train is 132. So let's say initial velocity is 132. I think I'll change the u is equal to 132 kilometers per hour. The final velocity, right? This train has to come to stop here. It stops here. So your final velocity is 0. So final velocity is 0. What is the distance you traveled? S is equal to 0.676 kilometers, right? So you have to find, so you applied the brakes here, right? So I told you have applied the brake. So this is a point at which you applied the brake, right? So you traveled through this distance and then stopped just before colliding, right? So the total distance you traveled is this much, right? So you know equations of motion, and of course it is assumed, if you read the question very carefully, it's a constant acceleration. Okay, if you notice this word, it's a constant acceleration scenario, which goes to show that this is a case of uniform deceleration. Okay, and remember, I have explained in my previous videos, if the body is moving in this direction, right, but the brakes are here, so this is a direction, it's a case of deceleration. So V and A, right, are in opposite direction. Now it's a case of uniform retardation, so therefore we will apply V square minus U square is equal to 2AS, and 0 square is equal to, I'm just getting it here, okay, so minus, let's say minus U square is 132 square is equal to 2A into S is 0.76, right? So, okay, so now you know what exactly it is going to come out to be. So this is 0 is equal to 100. This is the minus sign, not equal to. So 0, and let me just redo this. 0 minus 132 square is equal to 2 into A into 0.676. Solve this and you will get A, and A is coming out to be with a negative sign. So 132 into 132 divided by 2 into 0.76, and you will get this answer in kilometers per hour square, for the simple reason that I've kept everything in hours. Generally, students tend to convert everything in meter per second, which is more smarter way of doing it. But I just wanted to explain you this, and that's all. So you get the answer, acceleration. That first part is done, right? All right. Now let's talk about the second part, right? Very interesting. The second part is your understanding of graph. So, see, in examination, a lot of teachers or examiners want to test your graphical understanding, because when you go for engineering or science or any other, like medical profession, graphs are very important. You should be able to, read the graph, and every graph has a story to tell, right? So what are we supposed to do now? We are supposed to draw the graph of the high speed train, which is decelerating, and there are two graphs which have been asked. So one is it stops, which is just avoids the collision, and second case is it is not able to avoid the collision. It goes and strikes the second train. So there, we have to draw two graphs. Okay, let me just show you the scenario. So the question is, you have to draw the graph of what? You have to draw the graph of S versus time, obviously. It's an XT graph, you can notice. So it's displacement versus time. And if you notice, there are two graphs he's asking. Okay, graph number A is is you to draw the xt graph, which is displacement versus time, when the collision is just avoided. Collision is just avoided. This is one. And of course, the situation number two, the second graph is xt when the collision is not avoided, right? So there is a significance. And obviously, if you come to think of it, when you were able to avoid the collision, your deceleration, which you just calculated, is good, right? So if you use this as an acceleration, actually it's a deceleration, the collision will be avoided, right? So this is the situation number A. But if your retardation is not good enough, you don't apply the brakes properly and your retardation goes down, you will continue to move and collide, right? So there are two scenarios we have to think about. So one is the acceleration is this much, and obviously the deceleration is less than this, whatever word you want to use. When I say acceleration, it is with a negative sign, so it automatically becomes deceleration. Now if you think of it, the acceleration and deceleration concept, okay, in terms of s versus t is the right, this is what you need to worry about, okay? So if you come to think of it, the only equation that links acceleration and the distance, and this is displacement and time. If you think about it, s is equal to ut plus half at square, right? Generally you're very used to, so this is your xt, actually xt, right? And this is a parabola, right? This is a parabola, and you have an initial velocity, right? So the train number uh, A, which is a fast moving train, has a, so it says assume, sketch the for the locomotive. So you have to draw it for both. Okay, you have to draw the graph for this, which is for the high speed train. So you have to actually make four graphs: high speed train, and this is your locomotive, right? So there are two: high speed train as well as locomotive. So we will draw both the graphs for each of the type of train it is. This is just a locomotive and this is the high speed train, right? Let me just start. So if you notice the st versus graph for the locomotive, right? If you think about it, the locomotive is applying the brake, right? Locomotive is applying the brake, right? So the so A has a value which is negative, and the speed is going to reduce constantly, right? So let me just discuss this with you, and let's do this in a format of discussion rather than me trying to preach you what it is. Use your mind also and think about it. How do you think about this? Now let's say the graph, is like this. I will just draw the graph, okay? Now what does it show you? That here there is a velocity, right? So let me just draw the concept of slope, right? So I will just draw the slope, and we're discussing, okay? I'm not solving it for you. I'm making you see the way it has to be done. So this is your slope, right? And then of course if you're accelerating, your slope changes. Let's consider some another point and say, okay, let's consider this point for instance, and let me draw a graph here also. So my graph looks like this, right? So my graph is looking like this. So let's say I assume this point, okay? And my graph is looking like this. Do you see that the slope is increasing? So the first line is like this. The second line has higher slope. So the higher you go, for example, if you consider this point, right? Look at the slope, right? The slope goes up drastically upward, right? So drastically the slope goes up. So which means the slope goes up, which means this velocity, okay, this velocity is v1, v2. These are instantaneous velocities. I've just drawn the slopes. Don't see them as vectors. You can make out that this is a case of acceleration. In an acceleration scenario, the velocity is increasing because the slope is increasing, right? But in your case, you have applied brakes, right? And I'm talking about the high speed train right now. High speed train. You have applied brakes. you and this brings an end to the 0.676, and some time elapsed in avoiding the collision. So we are drawing which graph? Avoiding the collision, which means you have to apply the brake. You don't have a choice but to apply the brake, right? And what are we doing it for? High speed train. This is time, this is displacement. Now this graph makes no sense, because this graph, the way I've drawn this, is showing you what? It is showing you a clear case of acceleration, right? So acceleration is not acceptable because it's a deceleration, because v1 is less than v2 is less than v3, or vice versa. The velocity is, sorry about that, is increasing, right? So this is the case of acceleration. Now let me draw another graph, and that may probably strike a chord with you, which is this. Let me draw this graph, and let's draw similarly some. So let me draw this. You can see the slope here is this. And as you progress, the slope, and if you go here, the slope is this, right? So you can see the slope, the slope is very high here. It becomes something like this, and then it becomes like this. Slope is decreasing, which means as the body is moving forward, the speed is going down. And this pretty much reflects the case of deceleration, because here the velocity 1 is greatest, velocity 2 is less, and v3 is even less. And therefore, this is the case of deceleration. Okay, so the only difference was, the shape of the parabola you drew. If you draw it upwards, and facing this side, this becomes a case of acceleration. If you draw the other way, this becomes a case of deceleration. So avoiding collision, situation number 1, you apply a brake successfully. High speed train, this is graph number A. All right, now let's talk about the other train, right? The other train, if you notice, I mean, there is nothing to talk about practically, right? What's there to talk about? Because the velocity of that brake of the train is constant, and so there is no acceleration, as in the locomotive guy is not going to apply any brakes, because the locomotive guy has no clue that there's a danger lurking behind him, and he continues to move on the with this normal speed or whatever is given in the question, right? So if you think about it, he's moving with constant velocity, has no acceleration or deceleration. So this guy, in the case of aversion of the collision, just continues to move with his own pace, doesn't give a damn as to who's coming behind him, and with a constant velocity and slope, of course, whatever is given as the velocity of the locomotive is, I think it's written in the question, we just used it when we subtracted 29, right? So the slope is 29. So if this is in kilometers and this is in hour, the slope is 29 kilometer per hour, right? So this is the constant. So this is the constant uniform, so to say, uniform motion only, right? So constant velocity, straight line assume, or constant speed, and this is it, right? So see the difference. So one graph is parabolic, which is this. The second graph for the locomotive, locomotive is how the way it looks is a straight line. This is situation number 1, straightforward, with a some amount of intelligence required on the front of being able to discern its deceleration, acceleration. But locomotive, I think, is straightforward. There is nothing in this, right? So this is your hours, and that's all. These are kilometers, straight line. Let's go to situation number 2. The collision happens, which means the brake is applied, but it is not sufficient, right? The brake is weak. Now, how do you exhibit this graphically is the challenge, right? And so let's say the brake is applied, and let me do one thing, comparatively, because you have to understand it. Let me make you understand how do you do this. You have a sense that the previous graph looked like this. And even in this case, when collision happens, right? So the collision happens, even in this case, if you come to think of it, the brake will be applied. The graph is going to look like this. The question is, will the graph be above this? Okay, or the graph will be below this. How do you decide this? So this is the case where the collision is avoided, right? No collision happens. No collision happens. Okay, and now we have to worry about a slow brake. The brake is very weak. Okay, it really is ineffective. It doesn't work, and we need to decide, which is what graph. So let me just show you. If you think about it, this is your speed here, and then I'm just drawing the slopes to show you this is another speed, and this is another speed, and then so you can see, I've drawn, and then let me just show you this, and then this slope, and then this slope. Now what we need to, okay, so not a great slope, but hopefully this looks better. If you think about it, is the the brake you've applied, this is deceleration for sure. All three are deceleration. Now the decision has to be taken, which one is a weaker deceleration? Is this the weaker deceleration, or is this the weaker deceleration? Which means the train really is failing to stop, and the speed is not increasing to the extent you wanted, right? If you notice this one, look at the upper graph. Here the speed is not really reducing. The speed is on this side, then speed. But if you notice the slope of this graph, here, the slope is like this. So which means the speed has gone down drastically, because the initial slope, in compared to the initials, this has turned quite a lot. So this is a case where if you notice this point, the slope is weak, right? It's low, and therefore you can safely say that the rate at which the velocity is decreasing in this situation is high. It's a very strong brake you've applied, and probably you will stop even much earlier than you anticipate, and therefore the distance you have covered is even less than 676 meters. So if this was your 676, you got to stop much below that. So maybe you covered less distance and you're able to stop because you apply such a high amount of brake. So your curve is like this. But if you notice this, the situation number 3, maybe we call it 3, this is a weak brake, right? The speed is quite a lot here also. The slope is good here, the slope is good here. And the rate at which the slopes are decreasing, is less. So which means it is not really stopping the way you want to. So I will say that this is the situation when the collision will happen, because your brake is very weak, right? And this is a situation where you don't avert, you actually stop your train much before the locomotive. So if this is your train, right, if this is your train and you have a locomotive in front of you, so if I talk about this situation number 2 here, you will be able to stop your the train much before the locomotive, right? So this is your locomotive, and this is your high speed train, and you can see there's a substantial gap between them, right? So because the brakes were applied very strong, so it's a very high braking system, whereas here low brakes, right? Pathetic low brakes, and therefore the driver is not able to avoid the collision. Now if you talk about the same graph for the locomotive, again locomotive has nothing in it, right? Locomotive has nothing in it, and you can notice one point which is more pretty, I don't know, but you can think about it. It's my interpretation of the question. So it is going with the same as usual. It's 29 kilometers per hour. This is your S versus T. This is kilometers and this is hours, right? 29. And then when the collision happens, the speed which it gets is increasing. So it further, the slope even becomes more steeper after the collision. Just a food for thought. It's not part of the question. The real question ends here. There is no change in the. So this is the point where the collision happens because of the poor braking applied by the high-speed train guy, and then it adds up to the speed and it moves more faster, right? Because the slope is higher now, it accelerates, right? And you can see one more point is that because I've drawn the so the curve is more like this, which is an acceleration curve. The deceleration curves are like this on a ST graph. So I hope you enjoyed this video, you liked it. What I liked about this question is the practical utility. This is used in insurance sector when a lot of accidents happen. The insurance people send some scientists and forensic guys who see who did what and whether the brakes were applied at time or was there a reaction time, was a driver sleeping or stuff like that. So a lot of practical utility. Excellent question if you want to learn about graphical physics. Also, you want to learn about graphs. You want to understand how do so I hope you enjoyed this. Thank you very much for your time, and I wish you good luck for your examination and look forward to meet you tomorrow with one more interesting video. Do not forget to subscribe because you're going to see some excellent videos coming your way. I have a playlist of kinematics on this. Don't forget to watch it also. Thank you very much.